All right, CNT140, we're continuing on with Chapter 7. So we're now at the section on fiber optic connectors. Since fiber optic connectors, or since fiber optic technology was introduced, numerous connector styles have been developed. Many. And each design was meant to be better performance, as far as reflectance, loss, etc., easier, faster to terminate, more inexpensive, etc. As things have progressed, things have tried to improve. Some have been better, some not, but it's kind of an evolution thing. There's been a number of attempts to try to standardize connectors, and originally the TIA 568 standard called for SC-type connectors, but as things went along, some manufacturers were able to produce connectors that worked better. So the standard took a step back and said, all right, as long as the connector meets an acceptable quality standard, then it can be a connector that's commonly used, if you will. So here was the the original standard called for SC, but now if you read the standard, no specified connector, 568 SC and other duplex designs may be used in addition to MPO, MTP, that multi-fiber connector, if you will. So opening up some avenue for development. The book showed you a couple historical ones. Here's the Deutsch 1000. This was basically like, think of it almost like a drill chuck, holding the fiber in place. And it was actually a mechanical connection in there holding the fiber in place to make contact with another fiber. AT&T Biconic connector. Again, this one you had ferrules molded around the fiber until the actual pin was developed and so forth. But this one here, next step in design. SC, this was kind of a big step, and that's why SC for a while was kind of put into the standard. This one, introduced in the 80s, now had a ceramic ferrule, the little ceramic ferrule coming out the end, the little white part sticking out on the end. This could be made cheaply, extremely stable with temperature, heating and cooling and so forth. Hardness was similar to glass, so it could be polished as well as the glass stub on the end. This readily adhered to the fibers using epoxies or other adhesives and so forth. So as we look down the road to today, pretty much all connectors use a ceramic ferrule. 2.5 millimeter was kind of the standard SCST, FC kind of thing. And then as we moved on to LC, that fiber, the ceramic ferrule dropped down to 1.2 millimeter diameter. So as we look now at the LC fiber, this is kind of the next generation. This had again, ceramic ferrule, 1.25 millimeters, and now we can basically have two fibers next to each other in roughly the space of one of the previous connectors. This tends to be one commonly used, especially for premise networking and so forth. This is a lot of the connection style you'll see as we're connecting switches and routers and so forth together. Here's just a close-up of the end of an SC connector with that ceramic ferrule. This is the larger one. This white part out here is the ceramic ferrule, and then in the very center, I have pointed to that little teeny dot in the center right above my pointer, is where the actual fiber stub is. That is the actual fiber in that ceramic ferrule. Now, if we look at kind of evolution of connectors, early fiber connections, a lot were ST. And that uses a little spring-loaded twist lock connector, again ceramic ferrule. This little twist lock connector would lock it in place. SC would kind of got used next. MTRJ got used for a little while, and the common one used now is LC. So if I just flip through these, here's the ST, the straight tip. There's the ceramic ferrule. This is a little twist lock connector that would lock onto the device port that you're connecting onto. Here is your SC fiber, again ceramic ferrule. This out here, square connector. There's actually a key on the top, so you could get it keyed incorrectly, and not just kind of jammed in the hole, if you will. And then here would be your SC fiber port. MTRJ, this actually had both fibers in one connector. This style got used for a while, especially some of the switch ports we had, some of the uplink switch ports we had were MTRJ. The good part about this was it was small and both fibers in one connector, so you didn't have polarity issues. You just plugged it in. The downside was you had to get both fibers aligned in there. So it's kind of like, think about getting two bullseyes going fiber to fiber. So fiber alignment was kind of challenging on that one. The common one we see used now is our LC, and this is a 1.25 millimeters smaller ceramic ferrule. But there's the ceramic ferrules, fibers going down the middle, and this is the common small form pluggable module that we would slide into a switch, and then this cable would plug into, just like we did in the lab room. The other one that the standard mentions is applicable is your MPO, your multi-fiber push-on, or your MTP, multi-fiber termination push-on. These connectors can get used as well, and there's 12 fiber like ribbon cable, if you will, and then here's a double stacked, 12 on top, 12 on the bottom. Those can get used, and then you often have a pigtail that it breaks out to individual pairs of fibers. Pigtail for that one. The book mentions the plastic optical fiber connectors, the Toslink and the Avago connector. Here you might run into these with some consumer electronics and that sort of thing. Connector popularity, as we said, SC and LC. SC was very popular for a long time. Right now it seems like the LC is the pretty popular choice, especially with your premise cabling with small form pluggables, patch cables, that sort of thing. Other one popular multi-fiber connector is your MPO or MTP connector. This is typically not field terminated, but if you have that bulk fiber connection, this could get used for breaking out the fibers, as we said before, into kind of this fan-out connection. Most connectors use ceramic ferrules, as we said, and I think it listed these earlier. Could be made cheaply, extremely stable with temperature, hardness similar to glass, and the fibers readily adhered to that ceramic ferrule with adhesives, etc., epoxy adhesives, and so forth. And there again is your ceramic ferrule with the fiber. That little dot in the middle is the actual fiber. If I break apart a connector, here's an SC on top, ST on the bottom. It shows you that's like here's the actual connector itself with the ferrule, the connector itself with the ferrule, and then this body snaps over top. This back here, this crimp tube is there to crimp onto the aramid yarn in the jacket to give you some strength. And then this is the strain relief boot on the back that keeps the flexing of the cable minimized and protection of that bend point. Here's a more close-up of the SC fiber kind of broken apart for you. And then here's the LC fiber broken apart for you. As we terminate in the lab room, we'll use the LC fiber connector, so we'll get to see that a little bit closer as we deal with that. And they mentioned the end of the connector, the different types of ferrule polishes. Some of these we mentioned as we were talking about loss earlier. But if I look down to early connections were air gap, there was a little tiny gap there. And as we said, with that, think of like two garden hoses like super close to each other, but not touching, there's going to be loss. There's going to be loss in there. And that air gap sometimes actually acted as a way to bend the light going from the glass to the air, different index of refraction. Beginning with ST and FC, these were now physical contact, PC, physical contact connectors. Were polished flat. This reduced the air gap, so reduced the loss in there. That helped with getting, more of the light from one fiber to the next one. Next evolution was polishing the end of these connectors convex, rounded, as we said before. That allows the two fibers, literally the core to touch the core, trying to get those two fiber cores to touch or be in alignment. Again, reducing the amount of loss from fiber to fiber. And then the angled physical contact, slight angle here, if you look, slight angle to the connector. And the idea there is light goes from this fiber to the next one. As it hit that angle, any of the reflectance would come back and reflect off at an angle. Actually, it'd probably be this way. And that light would be going out towards the cladding and not back on the core and causing some additional signal loss. Now, as we look at connectors, the color code on the body of the connector lets you know the type of fiber it's connected to. So your beige body there, OM1 fiber. Your black body there, OM2 fiber. Aqua body here, OM3 or OM4. Okay, and then as I look at the blue and green, we're thinking your single mode connection now. So the connector body is letting you know the type of cable, the fiber cable that's in there. Multi-mode connectors, we can typically field terminate with those, with these different types of connectors. Pretty common, and we'll even show you a style in the room. Single mode are usually installed by splicing on a factory-made pigtail onto the fiber. So the actual ceramic ferrule and fiber are factory installed, and then you're literally just connecting the two fibers together, almost just splicing the fibers together. This now can give you a low loss connection. Typically, though, this is done in a factory environment, polishing on the fiber and so forth, but you can fusion splice on a pre-terminated connector, if you will. Connectors can be installed directly on most cable types, especially your type buffer fiber. That's the type we'll be doing in our lab room. But as I do this, I typically need to support the cable, whether it be in a patch panel or a splice tray or something like that. I need to protect the fiber because it is rather fragile at that point. I need some protection for it. Connectors can be installed directly on most cables here. 250 micron buffered fibers in loose tube cable. I will need a fan out kit. So here the fiber comes in, and each of the 12 individual strand fibers go down their own little protective tube to the termination point, and that little tube is protecting that fiber that has broken out from the bundle. Cables can be pulled with connectors on them. If you know the exact length of the connection, I think we talked about this with our bid spec project, you can actually order a cable with the connectors put on in the factory. And then I can pull them through interduct, but I have to do some care as I'm doing that to protect the fibers. I need to use some sort of pull eye to protect those connectors as it's being pulled through interduct. And I think we talked about that or even showed that in the lab room already. Several different types of terminations are available for multi-mode fiber. Single mode fiber requires different connectors and polishing techniques and are best done in a factory environment, or as we said before, we can do splice on connectors where the actual fiber connector is terminated and we're just splicing on that pigtail hanging off there onto the fiber that we prepare. And that can be done. All right, the first style of termination is adhesive style termination. This can be epoxy or even some of the fast curing adhesives. Follow the termination procedures, use only the specified adhesive so it bonds and so forth. If the adhesive fails, because I do my own little thing, the fiber itself might actually piston. It might stick out the end of the connector or even retract back in. So care must be taken. After it's adhesived in, then we need to polish the end of the fiber to be flat with the end of the ceramic ferrule, or convex if we're rounding it, if you will. Epoxy polish terminations. Pretty much all of your factory terminations are done in this manner, where you're actually epoxying the fiber into the connector. Provides a reliable connection, low loss, low cost. The epoxy can be set overnight or cured in an inexpensive oven. They remind you, don't use a heat gun and don't use a hot melt oven. Those temperatures are not correct for it. Here is an example of here's a fiber coming into the connector. Sorry, the phone ringing there. Here's your jacket. Here's the tight buffer. That is stripped off. The fiber is fed through the connector here, and you see it sticking out the end. This is where it would be adhesive or epoxied in place. Once it cures, then this is cleaved off and polished back to the end of the connector. So that process ends up looking like so. Strip the buffer off, epoxy fit the fiber into the connector, let it cure, scribe the end of the fiber stub that's sticking out, cleave it off, break it off, and then polish it. Basically polish the fiber back flat with a ceramic ferrule using a polishing puck and polishing medium to basically, I hate to use the word sand, but kind of buff it back so it's flat with the end of the ceramic ferrule. We'll keep going in the next podcast.